Okay, so now it's time to learn, I guess what I like to call the 6 differentiation formulas. No one really likes to memorize because of how weird they are. So that's what we're going to do today, derivatives of inverse trig functions. And we're going to actually take what we learned in the last mini unit, implicit differentiation, to actually prove what the derivative is. So this video is basically aimed at proving what the derivative of the inverse trig functions are. And I want to make 2 notes. So the first note is kind of a quick review, right? If you have a function and you place the inverse function inside of that function, you basically return x, right? Whatever the input is here. So basically these two cancel out and you get x, right? And then this also works for this case. Because they're inverses of each other, you just get whatever x is. And that's very key to this, I guess, derivation or proof, if you want to call it that. And the other one is about notation. So on your calculator, you probably see the inverse as this, right? If I were to input something here. Another notation people like to use, and I like to use, is this, arc sine of x. And I kind of like this notation better because of the power, right? If you have sine to the -1, it's kind of weird, especially because we sometimes use sine squared a lot. So this is the other notation that we use, and same with cosine. You just basically you add arc in front of the name. So arc cosine, arc tangent, arc secant, arc cosecant, and arc cotangent. So if we were to combine these two notes together, if we were to take the arc tangent of the tangent function, it simply just returns x, right? So that's the 2 notes that I want to take note of. So let's actually start the proof now. I want to define y to be arc sine, right? And we want to precisely find y prime, right? So that's our question mark for this proof. What I want to do here, this is our first step, is actually take the sine of both sides, right? We can do that because we're doing it to both sides. Sine arc sine x. And remember from our just like quick review, these functions cancel each other out, and you're left with x is equal to sine y. And now we have something called an implicit equation because it's not defined as y. So we want to actually use implicit differentiation when we find the derivative of both sides. So from this, we have to use implicit differentiation on the left-hand side, which from this case is kind of like a chain rule example. So the derivative of the outside, keep the inside the same, and you want to multiply by the derivative of the inside, which is y prime. And then the right-hand side is actually really simple. Derivative of x is just 1. So our next step is to just solve for y prime, right? That's the implicit differentiation method. So now we have 1 over cosine y, and this is still kind of implicit in a way because y is not cosine of x, it's cosine of y, so we're not completely done yet. Our job here now is to try to get this in terms of x, and we're not going to do a bunch of like weird identities that no one knows. We're actually going to use a very common one. The sine squared of y plus the cosine squared of y is equal to 1. This is known as the Pythagorean identity. And where y is just any input, I can put any variable there, but y I put y because of the context we have right here. So if I were to solve for cosine squared of y in this Pythagorean identity, I would get, let me just write out all the steps. Cosine squared of y equals 1 minus sine squared of y, or cosine of y is equal to the square root of sine squared y. So let's make that substitution right here. And then we'll see why I want to exactly do this. Sine squared of y. So we have this weird thing in terms of y. Why on earth would I actually do this? Let's look at the original statement actually right here when I canceled it out. I made the statement that y is equal to, sine of y is equal to x. We actually have this term right here, right? Sine squared of y. So in other words, let me just rewrite it quickly like this, right? In other words, it's like that. So I can actually just substitute x here because I made this statement here earlier in my proof. So y prime is equal to 1 divided by the square root of 1 minus x squared. Yeah, and this is a very weird formula, right? So this is the derivative of arcsine, arcsine of x with respect to x is this, right? It's a very weird formula, so it's kind of weird to memorize. So, but you do actually have to memorize this one, unless, or if you really don't want to memorize this, you can go through this whole proof. So it's your choice. The next one I want to do is the derivative of arctangent. We're going to skip arccosine for a very specific reason, and we'll see exactly why towards the end of the video. Y equals arctangent of x. So again, we want to do a very similar process to the sine one. We want to take the tangent of both sides. So if we take the tangent of arctangent, we get x, right? So I'm going to make this statement right here. Tan y equals x. And kind of like this step is the important part, because we made a statement here of what x is equal to, so we can always convert back when we need to. And that was the same theme in arcsine, right? We made this statement and we ended up using it later. And then, so now back to the problem. We differentiate both sides with respect to x. This is the implicit differentiation. I'm going to just do this one right away, so it's just 1, right? I'm going to keep it here actually. So we want to find the derivative of tangent of y. This is implicit differentiation, kind of like chain rule. So the outside is secant squared of, keep the inside the same, and then you want to multiply by that chain. And then we want to solve for y prime. Not too difficult. And then like the last one, we want to use an identity, and the identity is kind of like a very similar one to the Pythagorean identity. We can actually derive it from the Pythagorean identity. So let me actually quickly do that. Sine squared, in case you, because I always forget what the, let me use y actually. I always forget what these identities are. Is it this one first plus that one, or is it the other one? So the way we do this one, we want secant, so the way we do that is by dividing all of these terms by cosine, all the terms. So that means we get tangent squared of y plus 1 is equal to secant squared, right? I always forget this formula because I don't know if secant's here, if it's tangent here, or where's the 1? Is it on the right or the left? So sometimes I just derive this on the fly. So we can actually substitute it here straight away because this is secant y and this is secant y. So we make this statement, y prime is equal to tangent, oops, that's not even close to what I meant to write. Tangent of y plus 1. And then remember our statement here, we can plug in what tangent of y is, right? So that's 1 divided by x squared plus 1. I'm going to rewrite it the way I prefer it, which is like this. I am actually going to skip going through the derivation of the third one we wanted to do, which was the derivative of arcsecant, for one specific purpose. I was kind of researching about this specific one, and there actually it's kind of like a dispute in math. It's kind of weird because there is a dispute in math about what the derivative of arcsecant is. I read in a book that this absolute value, some books actually have this absolute value and some don't. And I guess the reason why is that they want us to actually know what the range and domain of arcsecant is, and because of the domain, one side actually defines it in a way such that the derivative is this, and another group defines it in a way that's actually this. It's kind of like a dispute. I don't know if they actually formalize what it is, but the one I think is used the most is actually this first one. So I'm just going to give this to you right here. This one's a hard one to remember because it's kind of like, unlike the arcsine, we have to notice like a small difference here. Specifically what's inside the square root, right? This is x squared minus 1, this is 1 minus x squared, so it's kind of confusing in this sense. You just have to memorize this one again. If you really wanted to look up a derivation, it's a very similar process of the other two, but it's just that the fact that it's a disputed thing, I'm not going to include it as part of this video. So now we want to look at a summary, so I'm going to write all the three that we know, and then we can easily find the other three. So I have a summary of what we found in the first part of this video, right? The sine, and then the arctan, and the arcsecant. Now we actually want to find the derivatives of arc cosine, arc cotangent, arc cosecant, and I wrote them in this specific way with the same colors for a specific reason. Kind of like with identities with trigonometric functions, there's actually identities for inverse. And I'm going to write the ones that I want to point out here. I'm actually going to write it arc cosine, just for this purpose, minus arc sine, and then arc cotangent. You don't have to memorize these identities, even I don't know them. I'm actually just copying it from somewhere, because I never actually seen a question or anything that uses this fact, but this is actually a fact. You can believe the internet. These are the identities specifically. Just notice that when we take this derivative, right, when we do d dx of this side and then d dx of this side, this actually goes away, right? All the constants go away, and then we're left with a negative sign of the derivative of arc sine. So actually, all these are just the negative versions of these. So if you're wondering where I just pulled this out of, you can actually go through the standard, I guess the standard derivation that I did above with all the other ones, but this is just so much easier to think about. Just know that's the opposite. And like I said, this lesson and these formulas are actually just a pain to memorize the first time you learn it, and it can only be memorized well and like comfortably with a lot of practice, because look at this, we have sine and cosine. We kind of associate the reciprocals being associated with each other, right? But these are not reciprocals of each other, sine, cosine. But these ones are actually reciprocals of each other, tan and cotangent. But then these ones don't follow that pattern, right? They're not reciprocals of each other. So that's another, I guess, flaw, or like another thing people don't like, is just memorizing which one's actually the negative version of the other. Right, the sine and cosine are together, tangent, cotangent, and then secant, cosecant are together. I guess you can just pair sine and cosine together, and then tan, and then something tan, and then secant and something secant, right? Because they have the secant in both of them and the tangent in both of these, and then just remember sine and cosine. But then also just actually remembering the order, right? 1 minus x squared, 1 plus x squared, and x squared minus 1 with the absolute value bars of an x term that's being multiplied to it. And then, like always, people like to put the chain rule examples, right? Not just arctangent of x is going to be like arctangent of like x squared, or arctangent of some product, or something crazy like that. So this is why a lot of people don't really like learning these or like memorizing these, because it's just a pain sometimes just to memorize these. But you either memorize these or you go through the derivation. That's the choice you have, especially in this a calculus class, right? If you really want to, you can derive them. They're actually not too bad if you know how to use implicit differentiation. But yeah, so I guess have fun with this. Any problems with these? Again, you can always submit a form if you don't know how to do a specific problem, and I'll probably make a video out of it, especially because a lot of people struggle on specific problems. Even though they kind of understand the general idea of the lesson, they just sometimes don't know how to apply it, and it usually takes someone to help them. So that's what that form is for. So that's the end of this video. We're going to be doing a lot of practice next video with these. So that's it.